Today we are going to try to come up with an equivalent idea to the chain rule, but for integration. For instance, even though we can integrate the square root of x, because this is just a power of 1/2 of x, we don't have any way currently to integrate the square root of x plus 1. We have this inside function that we can't really get around. There's no way to kind of expand out the square root over this sum. So how do we deal with it when we have a composition like this? Well, since integration is just the reverse of differentiation, it makes sense to start with the chain rule and try to turn it around. Remember, we have our formula that the derivative of a composition, so g of f of x, is equal to the derivative of the outside function with just the original inside function in it, times the derivative of the outside function. Or the derivative of the inside function. If we turn this around and write it as a formula for integrals, we basically have the integral of the thing that's not inside the differentiation operator is now inside the integration. So they have the integral of this side is then equal to this. Well, that plus c at least. We always have that additional constant possibility there. But that's not too big of a problem. If we can get this part of it, the g of f of x part, then the plus c is just kind of tacked on. Unfortunately here, as we can kind of already see, the integrand is pretty complicated. Not only do we have a composition of g prime and f, we then also have to have this f prime of x in there somewhere. In a particular situation, we would have to identify not only this composition, but also some other piece. That might not be such a big problem when it comes to like the square root of x plus 1, because the derivative of the inside here is just a 1, but it would definitely be a problem if we're trying to take, say, square root of x squared plus 1. Now the derivative of x squared plus 1 is not in the integral, and so it would not match this particular form. We'd have to have, say, a 2x in here. Now the 2x would be the derivative of the inside function. This would be kind of the optimal situation that we'd like to have. It's also maybe a little unclear exactly how we necessarily interpret it in this form. We'd actually have to come up with an f, we'd have to come up with a g, and make sure we had everything correct. What we can do to kind of get rid of some of that confusion is just writing things a little bit differently. What we will do is, instead of identifying functions f and g, we're going to replace the inside function by a variable. It's kind of standard to pick the letter u for this variable, or, well, it's kind of standard to use u, but we can pick any letter that hasn't been used already. So I'm just going to say let u equal f of x. So u is some expression in terms of x. Then in our integral, we have g prime of u, but then we also have this stuff here. What is this stuff at the end? Well, this is actually something we've seen before. It's what we call the differential. Remember, anytime we have a variable equals a function of another variable, we can differentiate that function and get the differential. Now, we didn't talk about this much in the past, but essentially it's what if we took du dx is equal to the derivative, just use that notation, and then interpreted du dx as a fraction and move the dx to the other side. So that's what we call the differential. It's actually very, very useful in this context, because what that allows me to do is change our formula from here, this thing here, into the integral of g prime of f of x, which is now u, this thing here, and then f prime of x dx is now just going to turn into a du. And that's going to equal g of f of x as u plus c. Essentially, this is just saying that the integral of g prime is g itself with a constant. It's pretty reasonable. The integration and differentiation should cancel each other out that way. It's just a matter of doing this substitution allows us to actually turn it into something that we know how to actually work with already. This process is called substitution. And the idea is that when we have an integrand where there's some inside function we would like to not have there, something we would like to simplify, we're going to follow some steps. We're going to, 1, set a new variable. Just going to use u. And a lot of times people will actually even call this u substitution because the variable u here is so commonly chosen. To some function. Or wait. Let's say to the inside function. So u equals f of x. We write out some equation like that. 2, we find the differential. This is just as simple as differentiating our function. Though technically there are a few times where we can use some little tricks in this part. We're not going to get into that right now. We'll kind of do the easier version of this for now, until we get used to it. Step 3, substitute u and du into the integral. And here specifically we need to make sure that we do one particular thing. Make sure there are no x's left. If there's any x's left over in your integral, then you haven't done all the substitution yet. There has to be no x's left over in your integral, or this isn't going to work. Sometimes you can actually have some trouble actually getting all the x's out, in which case maybe you did a substitution that wasn't good. Not all substitutions are going to work. Some will work better than others. That's going to come down to playing around with things, getting used to how things work. Step 4, integrate with respect to u. So theoretically, at this point, you've got it down to the integral of g prime. Hopefully, you know how to you can actually see what this function is in terms of as the derivative of another function, and you can actually do the integration. But it's basically going from what we have over here in terms of u and putting it in terms of just actually doing the integration part. And the 5th step, because once we actually do this integration, notice over here we do have u's still in the formula. We want to put those back in terms of x. We don't want to say the integral of something that only has x's in it is something that only has u's in it. We actually do want to have everything back in x's at the end. So substitute x back in. Again, this process doesn't always work very easily. Specifically, like I mentioned before, we might not have, say, this 2x in here. That would actually allow us to actually do this integration using substitution. There can be some issues there. So I'm definitely not saying that everything here is going to work very smoothly. In fact, this is not nearly as easy as using the chain rule itself. Integration can be a game of kind of trying stuff to see what works. And to get to the point where you can predict what things are good to substitute takes a lot of practice. There are also a bunch of substitution tricks that people have come up with over the years. Those are actually usually covered in Calc 2, so we will not be getting to those in this class. But the moral of the story is that while we learn how to differentiate any function that is made out of powers, exponentials, and logarithms, don't expect to be able to integrate all these functions. But don't be afraid to try stuff either. This is all just kind of a try things until something works. Of course, it's probably a little tricky to see exactly how things are supposed to work just from the explanation I've given so far. So getting into some examples is going to help you out a lot. Let's work on problem 10. Here we have the integral of x minus 3 to the 3/2 power. So this is like our square root of 1 plus x from the first page, except now it's a 3/2 instead of just a 1/2, and we have a minus 3 instead of a plus 1. But the idea here is the same. We have an inside function of x minus 3, and it'd be easier if that was just a u, if that was just a single variable. So what I'm going to pick is u equal to x minus 3. I want that x minus 3 to just be a single variable. I also need to find the differential. I just differentiate x minus 3. I get a 1, but that's 1 times dx. Do not just write du equals 1. That's not correct. So now I put these into my integral. Basically, the x minus 3 here becomes a u. Still have that 3/2 power. The dx, I notice here that we have dx is just du, so I can just put a du in there. And now, this is just an integral of a power. I know how to do that already. We have a power rule for integration. Remember, we raise the power, the 3/2, by 1. We add 1 to that. That gives us a 5/2. We divide by that new power. So dividing by 5/2 is the same thing as multiplying by 2/5. And I need to not forget my plus c at the end. And now here comes the last step. We don't want to have u's left in our answer. We want to put everything back into x's. So in each place I have a u, I need to turn that into an x minus 3. In other words, this is 2/5 times x minus 3 to the 5/2 power. And so that is the integral of this thing that we had before. What if we have something a little more complicated than just a linear thing? U equals x minus 3 is actually pretty simple. What if we have something like in problem 17? Here the integral of 6x over 3x squared minus 5 to the 4th power. So here we have stuff that's outside of this power. We have stuff that's inside that power. How do we deal with it? Well, it would be nice if the 3x squared minus 5 was just a single u. So that's what I'm going to try. I'm going to set u equal to 3x squared minus 5. That would mean that when I do this substitution, I'll just have a u to the 4th in the bottom. But I have to deal with all the other x's in here. So I have to take the differential. So the derivative of 3x squared minus 5. Well, the 5 minus 5 goes away. We have a 6x. Of course, that is times dx as well. That means in order to do this substitution, I have to find not only to replace the dx here, I also have to have a 6x in my particular integral to actually work with. Well, that's exactly what I have here. So they gave us a nice simple example here. So the 6x times dx, all of that is going to be replaced by a du. So I just have a 1 on top and a du at the back. Now I can actually do the integration. All the x's are gone, so I have everything in terms of u. 1 over u to the 4th power, that is actually just a power of u. We can go ahead and actually turn that into u to the negative 4 power. We can integrate u to the negative 4. Remember, I add 1 to my power, so negative 4 becomes negative 3. I do have to divide by the new power, so divide by negative 3, I get a negative 1/3 in front. Of course, I do need the plus c as well. I want to put everything back in terms of x, so this u that I have here is going to change back into a 3x squared minus 5. So I saw the negative 1/3, but now I have a 3x squared minus 5 to the negative 3 power. And if you really want to, if you want to put it back in the same way we have here, where it's a fraction, remember, this to the negative 3 power just means that this is to the 3rd power on the bottom. So I can write this as negative 1 over 3 times 3x squared minus 5 cubed. Of course, this last step isn't really necessary most of the time if you're just okay with it being a negative power. But the point here is none of this would have actually worked unless we had that 6x on the top. If we had, say, the integral of 1 over 3x squared minus 5 to the 4th power, we could try making the substitution of u equals 3x squared minus 5, but when we try to do the differential part, we wouldn't have that 6x in here to actually work with. So not all substitutions are going to work. It worked just fine for this particular integral. It's not going to work just fine for this one. And I'll show you a few cases where that's not a big problem, but for this one it actually kind of turns into a big problem. Let's say it doesn't work here. Let's do another example like this one. Let's take so in problem 22, we have the integral of t to the 4th power times the cube root of t to the 5th minus 9 dt. So of course we're not using x's here, we're using t's. That's not really going to change anything about the process. But the idea here is that we have this t to the 5th minus 9 that's inside the cube root. We would like that to just be a single variable. So let's try that and try just setting u equal to t to the 5th minus 9. If we do that, we do need the differential. What is the derivative of t to the 5th minus 9? Of course, the negative 9 does go away. T to the 5th, we have to use our power rule. We get 5t to the 4th. But then we also have to multiply by dt. So when we do this substitution, we're going to have a cube root of u, but we don't have a 5t to the 4th dt. We only have a t to the 4th dt. What about that 5? Well, it turns out that when we have a constant like that, it's not a big deal. What we can do is just do some algebra over here with our differential. Essentially, if I divide this equation by 5, I have that 1/5 of du is equal to t to the 4th dt. I can replace the t to the 4th times dt with a 1/5 du. Since there's no t's in here, that's not a big problem. So in fact, I'm just going to put a 1/5 and du. This thing, by a substitution, we can do it that way. And in fact, this is a very common thing to have to do. That you have an extra constant that doesn't appear in the actual integral, and you have to move it over to the other side. We'll actually be seeing that in a couple places later on. Now, when we do actually have those constants that get moved over, a common thing to do is also just move them completely out of the integral. Remember, when we have a constant times a function, it's the same thing as the integral of that constant, or that constant times the integral of the function. I can just pull any constants inside out of the integral. So a lot of times I'll just go ahead and do that. Instead of writing the 1/5 inside the integral to begin with, I would just immediately move it out in front. To integrate the cube root of u, I remember that the cube root is a 1/3 power. So we have 1/5 times the integral of u to the 1/3 power du. We use our power rule. Remember, we add 1 to our power, so 1/3 plus 1 is a 4/3. We still have that 1/5, but now we also need to multiply by the reciprocal, or divide by 4/3, means that we multiply by 3/4. And then don't forget your plus c. Well, 1/5 times 3/4 is going to be 3/20. We want to replace the u back in terms of t. So anywhere we have a u, we need to turn it back into t to the 5th minus 9. And that's going to be to 4/3 power. I don't really see any point in turning this into a cube root again. We'd still have to have the 4th power at some point. So I'll just leave it as to the 4/3 power. But the point here was mostly about the fact that if we have these additional factors in our differential, they're not a big problem as long as they're constants. If we say if this was a t to the 3rd in front, and the fact that we had a t to the 4th in our differential, the fact that we had different powers there would be a problem. We couldn't say take a 5t and divide it over to the other side to get that 1 over 5t du is equal to t cubed dt, because that extra t over here would be a problem. Make sure that when you're doing stuff like this, it's just constants that get moved over, because we cannot have any t's left over after we've done the substitution. All right, another problem, problem 36. Here we have the integral of 5x minus 3 to 2/3 power. Now this is maybe a slightly easier problem than it was in the previous one. There's no extra powers inside of it here. We just have a linear thing inside of our 2/3 power. Those tend to actually be pretty simple to do. But we still like to change everything that's inside here into a single variable. We'd still want to say let u equal 5x minus 3. We do need to take our differential. When we differentiate 5x minus 3, we get 5. So du is going to have to equal 5 dx. Notice we don't have an extra 5 in here anywhere. So just like on the previous one, we're going to have to move that 5 over to the other side. That 1/5 of du is equal to dx. That means our dx is going to be replaced by 1/5 du. So here, this is going to be u to the 2/3 power. The dx is going to become a du, but with an extra 1/5. And I'm just going to stick the 1/5 out in front. It really doesn't do much inside of the integral. It's just kind of there. And then we just follow our steps from before. We're using the power rule here, our new power. When we add 1 to 2/3, we get 5/3. We then need to multiply by the reciprocal. The reciprocal of 5/3 is 3/5. And we have to add in a plus c. Finally, we go ahead and combine these two fractions. 5 times 5 is 25. U gets replaced back with the 5x minus 3. And we still have to the 5/3 power. And we still have the plus c. Next, let's take a look at problem 42. Here we have the integral of x squared plus 3 over the cube root of x cubed plus 9x dx. We have an inside function of x cubed plus 9x. We would like that to just be a single variable. But we've got all this other stuff in here. So whether or not that will work, we'll have to see. But it doesn't hurt to try. So we see something that we'd like to substitute, and we go ahead and just try it out and see what happens. Now when we set u equal to x cubed plus 9x, when we differentiate it, x cubed becomes a 3x squared, 9x becomes a plus 9. All of that needs to be multiplied by dx. You might notice here that we do not have a 3x squared plus 9 dx in here, but we do have something pretty similar. We have an x squared plus 3. In fact, if we go ahead and pull 3 out of here, we would have x squared plus 3. So let's just go ahead and divide both sides of this equation by 3. 1/3 du is equal to x squared plus 3 dx. So in this particular case, we got kind of lucky. Or at least, if this was just something randomly that we were given, then we get lucky. Of course, the book kind of set this up for us to do this initially. But the point here is that everything in this cube root becomes just a u. The x squared plus 3 dx just becomes a 1/3 times du. Of course, I'm going to go ahead and put the 1/3 out in front. So by doing this substitution, we turn this into a much simpler looking integral. Of course, the cube root of u on the bottom is really u to the negative 1/3 power. And now we can use our general power rule, our power rule for integrals. The integral of u to the negative 1/3, we add 1 to that power, so negative 1/3 plus 1 is a positive 2/3. We need to divide by the new power. Divide by 2/3 means that we multiply by 3/2, and then we add in a plus c. We can simplify that fraction. The 3's cancel out actually. We get a 1/2. We need to replace the u back in terms of x's. So instead of u to the 2/3, we have x cubed plus 9x to 2/3. And we solve the plus c. So this is an example of a case where our differential actually looked a lot more complicated than the previous ones. All the previous ones were just a power of x with maybe a constant in front of it. Here we can see that we can actually have more complicated expressions, but the chances of finding that more complicated expression in your integral might make the difficulty a little bit higher. We'd actually have to have this x squared plus 3 kind of situation in our integrand before we can actually make that substitution. So, for instance, this same process wouldn't have worked if this was x squared plus 2 on the top. Even though it looks very similar to what we have here, the substitution will not work. So there's little minor modifications that make it seem like it shouldn't actually change much, might make the integration significantly different. Let's go ahead and do one last example. Let's do problem 50. So this problem has slightly different instructions. It says, in exercises 47 through 50, find an equation of the function f that has a given derivative and whose graph passes through the given point. So this is very similar to what we had before, where all we're trying to do is actually find the plus c at the end. So they're giving us a function, or the derivative of the function, f prime of x is equal to x times the square root of 1 minus x squared. This is our derivative of the function. And we know that the function has to pass through the point 0, 3/7. So that means our function, f of x, is going to be the integral of this, at least for some particular plus c at the end. But the actual integral is going to have to be done through a substitution. We have an x on the outside, but we have a 1 minus x squared on the inside. We can go ahead and try to turn that inside function, the 1 minus x squared, into a single variable. We find the differential. The derivative of 1 minus x squared is negative 2x. We have to multiply that by a dx. Well, we do have the x dx in there, so that's a good sign. All that's left is the negative 2, which is not in there, but we can go ahead and divide that to the other side. So the x dx can be replaced by a negative 1/2 times du. In fact, I can go ahead and pull the negative 1/2 out. So negative 1/2 times the integral of the square root of u du. In fact, we can go ahead and immediately turn this square root into a 1/2 power. Now we go ahead and take our integral. U to the 1/2, we raise that power by 1. 1/2 plus 1 is a 3/2. We need to divide by the new power, the 3/2, which means that we multiply by the reciprocal of 2/3. We do have a plus c in there. We're going to have to find out what that plus c is in a moment. But let's go ahead and finish turning this into something in terms of x's. Negative 1/2 and the 2/3, the 2's actually cancel each other out. We have a negative 1/3. This u is a 1 minus x squared. And we saw the power of 3/2. And plus c. Now, how do we find the plus c? Well, remember, we have to pass through the point 0, 7/3. This means that f of 0 equals 7/3. If I plug 0 into my function, I should get 7/3 out. So let's go ahead and plug in 0. That means on this side, f of 0 is 7/3. On this side, we saw the negative 1/3. We have a 1 minus 0, so a 1 to 3/2 power. But of course, that just is a negative 1/3. And then we have plus c. In other words, we have c minus 1/3 is equal to 7/3. If we add 1/3 to each side, 7/3 plus a 1/3 is 8/3. That means our function, f of x, is equal to negative 1/3, 1 minus x squared to 3/2, plus our c value that we just found of 8/3. So finding the c didn't really change too much about how we actually approached the problem, just added an extra step at the end. But the point here is that how we can actually tackle a wider range of functions, in things that actually do have stuff inside of other powers, inside of square roots, inside of cube roots, eventually in coming up in the next section, inside of exponentials and logarithms, things like that, and how we actually approach doing stuff like that. So that's all we have for today. Like I said, in the next section, we will talk about exponential logarithms in terms of integrals. So we'll get more functions to work with. So I'll see you then.